see. Okay. Yep. So far we've had 1.1, 1.2, and 1.3. And what we're looking at today is 1.4. 1.4 is functions. Introduction to functions. Many everyday phenomenon involving two quantities that are related to each other by some rule of correspondence is going to be considered a relationship, a correspondent relationship. We do have formulas, functions, like this here represents a special kind of relationship that matches each item from one set to exactly one item from another, which is called a function. So, talk about temperature. So, it is considered a function if each element in A must be matched with an element in B. Some elements in B may be matched, or some elements in B may not be matched with any element in A. Two or more elements in A may be matched with an element in B. An element in A cannot be matched with two different elements in B. So, vertical line test. Vertically, or verbally, numerically, graphically, algebraically. Different ways we can check it. Determine whether a relation is a function. You must decide whether each input is matched with exactly one output value. When any input is matched with two or more output values, the relationship is not a function. So the input value x is the number of representatives from a state. The output value is the output value y is the number of senators. So we have to determine if this is a function or not. Well, what do we think? Is this a function or not? Well, this verbal description does not describe y as a function of x regardless of the value of x. The value of y is always 2. So if we picked Oklahoma as the x, well, Oklahoma is going to have 2 representatives. We can't have one x for 2 y values. It's not a function. Let's look at the table. So our input, we have 2 to 10, 2 to 11, 3 to 8, 4 to 5, 5 to 1. Is this a function? Does not describe a function because the input value of 2 is matched to 2 different y's. It is not a function. Is this graphically this here a function? It does. Because even though we do have this point here, negative 1, 0, and 1, 0, we have the same y value, that's fine. We can't have the same x going to the same y value. Because that would be like this here. Because this does not pass our vertical line test. If we draw a vertical line and it crosses the graph or the points at more than one spot on that line, it is not a function. Representing functions by set of ordered pairs is common in discrete mathematics and algebra. However, it's more common to represent functions by equations or formulas involving two variables, y equals x squared, where x is the independent, the one we change, y is the dependent. Y depends on what we plug in for x. One's what we plug in, one is what we get out. Independent is the one we plug into the function. Our dependent is the output, what comes out of the function. The domain of the function is the set of all values taken on the independent variable. The domain is our x values. The range is the output, is our y values, the corresponding y values. The domain is the x values, the range is the y values. Domain is what we plug in or what we can plug into the function. The range is what we get out. And it's a set of all numbers that work for that function. When using an equation to represent a function, it's convenient to name the function for easy reference. For example, y equals 1 minus x squared describes y as a function of x, or we can say f of x equals 1 minus x squared. So we can talk about more than one function at a time. The symbol f of x reads as f of x. Function notation. And we could denote values and solve for values by using this function notation, saying f of -1, f of 0, f of 2. We're plugging in those values back into the function. So for this here, 3 minus 2x. So if we said for f of -1, apparently I'm going to draw a circle. So if we start off with f of -1, we'd plug it in. 3 minus 2 times -1. Well, that's going to equal 3 plus 2 equals 5, because our -2 times -1 is going to make it +2. So we get 3 plus 2, and 3 plus 2 is 5. We can do the same thing with f of 0. So that'd be 3 minus 2 times 0. We're just placing x with 0. 3 minus 0, which is 3. F of 2. So we replace x with 2. We're replacing every x in the function with 2. For these here, we only have one x value, so we only replace it in its one spot. And our -2 times 2 is -4. 3 minus 4 is -1. And that's it. So we plug these in and evaluating for these values. That's all we're doing. We're just plugging in the values of x to evaluate. Although f is often used as a convenient function name, and x, it's often used as the independent variable for other letters. So most of the time we use f of x. We can use f of t, g of s, doesn't really matter. It's just whichever they pick. Well then. Okay. Consequently, the function could be described by this here, where we just have boxes. And we can plug whatever we want into these boxes and solve for that there. And if we have a function with more than one equation, we call it a piecewise defined function. It's comprised of more than one function. So this here would be considered a piecewise function. And we consider it a piecewise function because, well, there are two functions that are making up this equation. Now, when we evaluate a piecewise function, so here we'll take f of -1 to start. We look at the x value and compare it to the two inequalities, and that will determine which function we use. So our x value is -1. So we have two options. Either x is less than 0 or greater than or equal to 0. So is x less than 0 or greater than or equal to 0? it's less than 0, which means since it's less than 0, we use the equation next to it. So for us here, we would say negative 1 squared plus 1. Negative 1 squared, negative 1 times negative 1 is going to be 1. And 1 plus 1 is 2. So f of negative 1 is 2. Questions on this here before we look at f of 0? Now with f of 0, we're doing the same thing. We're looking at the two inequalities. Is 0 less than 0, or is 0 greater than or equal to 0? Since 0 is greater than or equal to 0, we use the second equation, our x minus 1. And for this here, it would be 0 minus 1. And 0 minus 1 is negative 1. So f of 0 is negative 1. Questions on these first two here? Let's look at the last one, f of 1. Is 1 less than 0 or greater than or equal to 0? It'd still be, yes, it'd still be greater than or equal to 0. So we're going to plug it into our x minus 1, which tells us that we have 1 minus 1, and 1 minus 1 is 0. Questions on our piecewise function? And they did the exact same thing we did. You got 2, negative 1, and 0. Now the domain of a function, we're not going to focus too much on it, but it's really what values can we plug into the function. Now for most functions, most of our higher degree polynomial functions, so that'd be any of our quadratics, the domain is going to be all real numbers. However, for our rational equations, it's not going to be all real numbers because whatever makes the denominator be 0 has to be removed. We cannot have a denominator of 0. So here the domain excludes values that result in a division of 0. Anything that's going to make this x squared minus 4 be 0. And if we solve this here, the two values that would make the denominator 0 is positive 2 and negative 2. So at those 2 points, it is undefined. There is not a value for it. So the domain can be written as negative infinity comma negative 2 at the union of negative 2 to 2 at the union of 2 to infinity, because we're trying to remove those 2 points. It's pretty much everything but 2 and negative 2. If we're writing this as a union. Inequalities is not any better to write this because we have to write all 3 as inequalities. Because it would be, as an inequality statement, we'd have x is less than negative 2 and negative 2 is less than x is less than 2 and x is greater than 2. We almost have to have 3 separate statements for this here. But essentially the domain is all real numbers except for 2 and negative 2. The other one that we have issues with is even roots, even radicals, so square roots, fourth roots, sixth roots, eighth roots, because what's inside the radical has to be positive, well, really a non-negative. The number inside of an even root cannot be negative. Now, it would be very tempting to say that it has to be a positive number, but 0 is not positive or negative. So it can't be a negative number. We'll pull this up and show this here, and I'll go back to the other one too, because once we see this graphically, we can kind of see a little bit of this. Alpha y equals enter 1 over x squared minus 4 graph. So where x is equal to 2 and x is equal to negative 2, we see that there is that split. It jumps from one to the other. There is no value there. If we look at the table, at negative 2, there is an error. It is undefined. And at 2, there's an error. It is undefined. We do not have a value at those points. Same thing is true with, say, the square root of x. We see that it does start at the origin and goes to the right. It increases. And if we look at the table, at 0, it is 0. At negative 1, because there is no real value for a negative radical. So with radicals, the domain, our input, is going to be whatever is going to make this value of x, or whatever values of x, going to make this be 0 or greater, or make it be positive. We need the positive. We need what's inside this here to not be negative. So for us here, it'd be x is greater than or equal to 0. Now there are some where we would have to solve to figure that out. We could say the square root of negative x plus 4, because again, what's inside has to be greater than or equal to 0. That's going to be the domain. Now to solve this here, we would subtract 4, telling us negative x is greater than or equal to negative 4. Lastly, multiply or divide by negative 1. And whenever we multiply or divide by negative, we have to split the signs. So here it's telling us that the domain is all the values of x that are less than or equal to 4. And if we graph this here, we do see that the x values are going to the left. And it's not so much that x can't be negative with radicals, it's that what's inside here, our final number before we take the square root of it, cannot be a negative. In general, the domain of a function excludes the values that would cause division of 0 or that would result in the even root of a negative number. But for the most part, the rest of them, if we don't have that, the domain is all real numbers. So if we looked at the domain of this first one, here it's going to be the set of points. Negative 3, negative 1, 0, 2, 4. Because it's our inputs. Are the numbers that go into the function, the numbers that work. B, since it's rational, we have to exclude any value that would make the denominator be 0. So that's the only value we can't plug into this. That's going to make x plus 5 be 0. Negative 5, because negative 5 plus 5 is everything else works, yes? So the domain is all real numbers except for negative 5. If we wanted to write it as an interval, we could do this here, because again, parentheses aren't included, so we said all this here. And or well, right there. Or, really in the previous one should have been or 2, because it's for the domain x is either less than -5 or greater than -5. It shouldn't be and wouldn't have made any sense, because there wouldn't be any overlap. Or, I think this is going to be Cooper's favorite. The domain we said was what? All real numbers, yes? So x is an element of real numbers. Except that's it. Because in set builder notation, that little the apostrophe, essentially that kind of line, not quite an apostrophe, but that line means except sub this out. It's all of these values except this. Because again, mathematicians tend to be lazy. Now, the next one, volume, is equal to 4/3 pi r cubed. I'm going to grab the graphing calculator. Y equals 4/3 pi, and we'll use x instead of r, but that is our variable. We get these values, yes? Well, we do have negative values, and we do have positive values, yes? So the domain for this would be what? R, because since I use r instead of x, has to be greater than 0. Well, what are we talking about here? The volume of a sphere, yes? Well, and for most of our consideration, we can't have negative volume. It starts breaking lots of physics laws that you'd have to get. Quantum mechanics and probably some of the upper level stuff might deal with negative space. But for us, volume of a sphere has to be positive. We have to have a positive value. So even though, yes, if we were just looking at the function 4/3 pi r cubed as a function, the domain would be all real numbers. But since we put it in a real world context, well, the radius of the sphere has to be greater than 0. And the last one we've kind of looked at already. It's just that what's inside the radical, this even root, has to be greater than or equal to 0. So then it's just solving this here. Telling us that the domain, our x is going to be less than or equal to -4/3, or we can say -infinity, comma 4/3. And this one here would be a bracket because it does include -4/3. That point does work. Or, no, it's not negative. Mess that up. Start moving too fast. Should be +4/3. Because, just to check, because our -3 times -4/3, well, the 3 and 3 would simplify, leaving us with -4. 4 minus 4 is 0, and the square root of 0 is still 0. Domain, because the function represents the volume of the sphere, the radius must be positive. Example C, note that the domain of a function may be implied by physical context. You would have no reason to restrict R to be positive values, but the physical context implies that a sphere cannot have a negative or 0 radius. Different quotient, f of x plus h minus f of x, 0. Not going to worry too much about difference, but that's it. Yes. So 19, 20, they give you 19, 21, 24, 29. They give you you're evaluating the function for the given value. So for 19, 2 of them are numbers, 1 of them is an expression, so you would plug that in and simplify with the expression. Same with 24 and 29, 31 and 35. 31, you're just completing the table. If they give you a table, you just need to plug in the rest of the values. 35, find all the real values of x for which f of x is equal to 0. Set it equal to 0 and solve. For 35, 37, and 39. 43, find the value for which of x for which f of x equals g of x. Set the two equations equal and solve. That's all that is for 43. 48. Don't do 48 or 49. I'm not worried about those. Or 51 or 52. Don't do those. Don't do those. And make sure to fix Scooper's paper. He comes back, you've added 20 problems onto it. McClendon changed it. He said it was 19 through 52 all.